Hi everyone, welcome back to the course. So this week we're going to complete our space planning tutorial based on subdivision by finishing off our floor plan layout generator and basically giving it the ability to not only understand the spaces that it's producing, but also the adjacency between those spaces. So in last week's tutorial, we completed the kind of subdivision process behind our generator, which allowed it to use the splitting logic recursively to start with a single space representing the boundary of our floor plan and subdivide it into any number of smaller spaces. And in order to optimize those layouts, we implemented 3 different objectives that told the algorithm basically how we value the layout of the space. And because we didn't yet have the ability to program those spaces or to evaluate how those spaces are related, we created 3 basic kind of formal evaluation criteria, which said that, in order to have the layout be a good design, the rooms have to be as equal in area as possible, the rooms have to be as square as possible in shape, and the room shapes have to be as close to rectangular as possible. And when we did the optimization, we saw that it tends to create kind of realistic looking layouts, but we didn't have that element yet of knowing exactly what the rooms were, if they're meeting actual programming criteria. So what we're going to do this week to finish off our floor plan generator is actually implement this idea of adjacency to have the spaces not just track their own shape, but to track where they are in the layout and their relationship to other spaces in the layout. So adjacency basically refers to tracking which spaces are next to each other in the plan. And of course, this is like a huge component of planning a space, right? When you plan a program in a layout, you want to know which spaces are next to each other. For example, you want the bathroom to be next to the bedroom, you want the living room to be next to the kitchen. Now, in order to track the adjacencies in our floor plan layout, we need to change a little bit about how our data is structured in the model. And here we're going to introduce an object-oriented approach to our Python script. So before, we were just working with shapes and curve boundaries, and we're doing all the splitting logic just in the geometrical level. But now what we're going to do is we're actually going to create new class definitions in Python to create 2 different objects that store all the logic of our layout. The first object is going to be a space, which is going to represent one of the subdivided spaces, and it's going to store its curve geometry of its boundary. And the other object is going to be an edge, which corresponds to one of the segments, the line segments, in between 2 spaces. So our layouts are not going to be defined by a collection of space and edge objects. So for both of those objects, we're going to implement a way for them to store relationships to the other type of object. So spaces will store edges as references to the edges that form its boundaries. And in a similar way, edges are going to store spaces which relate to which spaces have that edge as a boundary. And with edges, there's always going to be 2 spaces because each edge splits 2 spaces between each other. And with spaces, there's going to be any number of edges that it can refer to. Now, what these edge objects are going to allow us to do is actually think about the relationship between spaces to each other. So we can actually start to traverse these objects because each object is linked to another one. So we can, for example, ask S1 for its edges and then ask each of those edges for other spaces that it relates to, and this will allow us to track the relationship between spaces that are adjacent to each other. So in a way, the edges are a kind of bridge between spaces so we can understand what the neighbors of each space is. So before we actually start to program these objects and relationships into our Python code, let's take a brief overview into how we're going to actually create these spaces and how we're going to store the relationships as we go through this recursive splitting logic. So as always, we're going to start with one boundary curve that's going to represent our first starting space. So if we can imagine having 2 different lists of objects, one for spaces and one for edges, Those lists are going to start with one space, right? We call it S1. And S1 is going to have its boundary curve definition, and it's also going to have a list of edges associated with it. And at first that's going to be an empty list because we haven't created any edges yet. And similarly, the list of edges will also be empty. So when we do our first division, no matter which direction we take that division in, we're going to need to start to create new objects for spaces and edges. And we're also going to start to modify these lists of related objects, right? So remember, in our recursive process, when we take a space and split it, we basically create two new spaces. So in the Python code we have right now, we create two new sets of curves, and those curves get added to our list that's tracking all the spaces we've created, and the space that we use to do the division basically goes away. You know, it's still stored in memory, but it's not passed down through the recursive process. So we're not going to change that part of the functionality. All we're going to do is we're going to take those curves as they're created and convert them to space objects. So we're going to have two new space objects, S2 and S3, and S1 is basically going to go away. And now we're also going to create, when we divide that space, that segment that divides those spaces, we're going to take and we're going to convert it to an edge object, and that object is going to store links to its spaces. So in the code, we need to start filling these lists, these links between spaces and edges, so that the two new spaces formed, S2 and S3, are going to store in their list of corresponding edges a link to this new edge, E1. And E1 is going to store links to its corresponding spaces that were just formed, S2 and S3. So at the first division, things are pretty simple, right? Because we have one space, we're forming two spaces, and there's a one-to-one link between the new edge and those two new spaces. Now things are going to get a bit more complicated when we start doing our further divisions. But the good news is all we have to do is figure out how to handle this case for one division. And after that, we're going to be able to apply that over and over again in our recursive process. So I'm going to show you how to do this in code in the remainder of the tutorial. But for now, let's just look at generally what kind of strategy we need to implement. So when we start writing the code, you understand why we're implementing certain features, and you can also go back to these slides as a reference to figure out, you know, why we're doing all of the different operations that we're going to do. So as a first case, let's look at the second division. So the second time we divide a space, and let's look at the case where that new division is in the same direction as the first one, which means that the new division does not cross and divide the old edge. The old edge kind of stays as it is, and we create a new edge separate from it in the space. Now, in this second division, we're taking S3 and we're consuming it to create two new spaces. So S3 is going to go away, and we have two new spaces, S4 and S5. And to make everything work, we're going to have to modify some of these data sets. So first of all, S3 is going to go away. It's still going to be in memory, but again, it's not going to be passed through the recursive process, so it's not going to exit our recursive function, and we're basically not going to have access to it again. But it is in memory, so we need to handle it in the data structures of our other objects. So first of all, we're going to add two new space objects to our list, S4 and S5, right? And when we consume S3, you see here it's linked to E1, right? Because S3 used to be in this space here. So we need to pass down that relationship to one of the two new spaces that are formed. So what we're going to do in the code is when we split a space to create two new ones, we're actually going to iterate over every edge that belonged to that space, right? So if we consume S3, we look, okay, it had an edge at E1, so we're going to take a look at E1, and we're going to assign it to the proper space by checking which space that edge actually falls on. We're going to use some geometry operations to do that. So through that process, we're going to identify that actually E1, which used to belong to S3, now has to belong to S4, and we're going to add it to S4's list. And in the same way, we're going to take E1, remove S3 as a reference, because we no longer want to have S3 in our data, and add S4 as the new reference. And this is really important because when we start to look at adjacencies, each edge only should ever store links to 2 spaces. Otherwise, you're going to have these kind of phantom connections to spaces that have already gone away, and it's not going to be very useful for us when calculating the adjacencies. Now for S5, we've gone through the list of edges, E1, and we found out it borders S4. S5 has nothing to do with E1, so S5 only gets a reference to the new edge, E2. And then we create E2 as a new edge in our data and link to it S4 and S5. Because that edge had nothing to do with any other part of the plan, we don't have to worry about adding any other references. It's only related to the 2 new spaces that are formed. Okay, so I'm going to go back a step to our first division, and now let's look at the other case, which is a bit more complicated, of what happens when we split S3, but that split line actually intersects one of our existing edges. Okay, so here's the case here, and what we want to do is, in addition to creating 2 new spaces and a new edge, we actually want to go ahead and split that edge into 2 new pieces, and we're going to create 2 new edge objects and basically get rid of the old edge, because we really need these edge segments to be individual. It's not that useful for us to keep E1 because it becomes confusing whether E1 relates to the adjacency between S2 and S4 or S2 and S5. So we actually want to create those 2 new edge segments and then assign one to relate between S2 and S5 and the other one to relate between S2 and S4. So we're gonna see how to do that in code, but basically there's a number of things we need to do. First of all, we're gonna take that edge and we're gonna split it. So again, we're gonna look through each of the edges that border the space that we're splitting. So we're gonna look at E1. Now we're going to test to see if that edge is split by the new split line. If it is, we're actually going to create 2 new edge objects. And as with spaces, we don't have to delete E1 from our memory. It's still going to be there, but because it will be taking out of these relationships of 2 spaces, it's basically never going to be referenced again. So it will exist in memory, but it basically will go away for our purposes. So once we split that edge into 2 pieces, we need to look through our data set and basically remove the reference to the original edge from the other space that bordered it, right? So we're working on S3, but we know that S2 is also linked to that edge. So we're going to take that edge out of its references, and we're going to add references to our 2 new pieces, right? We know if S2 bordered E1, and we took E1 and split it to create E3 and E4, we now know that S2 should be linked to E3 and E4 as well. Then we're going to take our 2 new spaces and we're going to figure out which piece relates to which space, right? Because this edge was split by the same line that created these 2 new spaces, we know that one of the edges will belong to one space and the other one will belong to the other. So we're going to use a similar kind of geometric operation to basically find out which space this edge lies on and then assign the right edge to the right space. So we're going to assign E3 to S4 and E4 to S5. And then just like before for our 2 new spaces, we're going to assign them both to the new edge that we form that actually split those 2 spaces, and we're calling it E2 here. Now in our set of edges, again, we're going to remove E1, so that's not going to matter anymore. And now we're actually creating 3 new edges. E2 is the split edge, so it has a reference to S4 and S5. And E3 and E4 are the 2 pieces created by the original edge that was split. And again, we're going to store a reference to S2, which is inherited from the original edge, and a reference to one of the 2 new spaces that were formed. So once we implement this logic and create these new objects in our model, we're actually going to have the ability to track which spaces are next to each other by following this list of spaces associated with edges and those edges associated with other spaces. And what we see here is the final result of our demo today. And we're visualizing those connections between spaces using these lines. We can also go in and create openings in the walls where those connections occur. We can even check the length of the edge against a kind of minimal length to make sure that we're not counting adjacencies when that connection is too small. And then finally, we can even create a data set of programs that we want to actually implement in our layout. So here we have a program list of spaces for a house. We can program their name, their area, and the adjacencies to other programs that those programs should be next to, and then set that as an objective in our optimization so that the model not only optimizes for spaces to be square and rectangular, but also matching specific area requirements by assigning programs to each of those resulting spaces, and even checking whether each space actually connects to the spaces that we wanted to connect to. So in the next few videos, I'm going to show you how to take the model that we've developed so far and implement these objects into the model so we can make a truly robust floor plan generator.